like one of those things where it's kind of like bittersweet to leave, like you're on vacation and then to come back, right? To come back to like everything normal, but there's something comfortable about being home. And so talking about equilibrium, it's kind of the same thing where we're made of molecules, we're made of atoms and molecules. And so it's only natural that we have a comfortable position, we have a comfortable place. And so this is what's going to end up happening when we go to talk about equilibrium. So let me give you an idea of like what we're doing in this unit, spend a little bit of time and like, I asked, Jin has some friends that go to Novi, and he was saying, based on what he said, we're pretty much at like the same place that they are, which is a good sign because Novi is kind of like a good meter, in my opinion. They're usually like really on top of their game. So if you guys have friends that go to other schools that are taking AP, if you wouldn't mind just asking to see like, how are we in comparison? Were you gonna say something?
My family friend goes to IA.
Yes.
And he's doing, I think, like IB chemistry.
Yes.
They're just now finishing up kinetics.
Okay.
But I'm not sure if they're going in order. I think we've done the same unit so far.
Yes.
But he's just now finishing up kinetics.
Okay.
As he's coming back, so.
Okay, good. Because you guys, you know what my like biggest thing, I think I told you guys this, that like, I have this fear that like, we don't get to where we need to, and I haven't prepared you. Like, that's just, you know, that would be like a nightmare for me. So as far as the practice tests go, obviously the more you do, you can fake it. I told you guys this, okay? So if you really wanted to, I give you the answers. You can just literally write whatever letters you want and then just mark off and be done in 10 minutes, right? And I know that that's not typical, like I don't think any of you are in that position, but whether you're taking the AP exam or not, it's still good practice for the future too. So your SAT testing is, my understanding is it's next week. So you guys, this is gonna happen really fast. Like this month is gonna fly. It's gonna go so quickly. So equilibrium, the nice thing is, I'm gonna kind of just like walk you through the pages here. We're gonna talk today a little bit about just like what is equilibrium and factors affecting, which is Le Chatelier's principle. My understanding is that you've done Le Chatelier's principle before, so it's kind of nice that you're just doing it like a second time. We talked about it a little bit when we were doing electrothermal. These are not in your notes. This is just, we're gonna do a no reports lab on Thursday. So it's gonna be one of those sheets, you just fill out the sheet as you do the lab and answer the questions. So there are different factors that affect it. Concentration, temperature, and pressure, we're going to talk about those, and then there's some practice problems there. On this next page, it talks about the equilibrium constant. We've already done this, so this kind of makes it nice. We've already done capital K. So remember, lowercase k is the kinetics K, and that K has units. Like, remember we said if it was like third order, it would be like molarity to the -2, seconds to the -1, for example. And with equilibrium now, it's simply products, concentration of the products over concentration of the reactants. It doesn't have any units. What it tells us is it gives us a position. So do you guys remember, if you end up calculating K and K is greater than 1, what does that mean? Products are favored. Who said that? Nice job, Daniel. So products are favored. If K is less than 1, then the reactants are being favored. And so the reactions are going to shift to try to come to an equilibrium where they're like most comfortable, okay? So the equilibrium constant, I talk about K. Now there's Kp and there's Kc. The reason for P is for pressure. So usually when we have gases, we don't talk about the concentration of a gas. We usually talk about the pressure of a gas inside of a container. And so that's why they use pressure. And you can switch between C for concentration and P for pressure using this equation. This equation's gone from the AP equation sheet. It used to be on there. Again, they get rid of those because people just lose sight. They get so into doing the math that they lose sight of the importance of like actually understanding the curriculum. Okay. Then this is just setting up K, so pretty easy. Like, remember you have to incorporate the coefficient, so it's raised to whatever the coefficient is. So we're back to that. We're like in kinetics, we don't do that. In kinetics, you had to figure it out experimentally. So this K is different. Okay, now I want you to see what happens here. Problem, 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 problem. Most of these notes are going to be doing problems together, okay? So when I taught physics, one of my biggest issues, so as a junior at state, I was in Lyman Briggs, and so I picked up a position as a TA, as a teaching assistant for physics. One of the biggest issues that I had with it was there were so many different types of problems that it was like, it was almost impossible to say, like, did you study all the problems? Because they could throw anything at you and you're like, okay, I've never seen this one before. Like I thought I had it down and now I've never seen this before. Something similar happens with equilibrium. David, you're like agreeing with me in physics. Who's taking AP physics? Are any of the problems ever the same? You guys are doing practice tests. They're like never the same, right? Like you're like, oh my gosh, it's a new kind of problem again. Like I've never seen one of these before. And so it's very like, that's kind of the challenging part about physics. So with equilibrium, let me just tell you that before 2013, the College Board had put so much emphasis on equilibrium. Number one on FRQs was always a full equilibrium problem. From beginning to end was an equilibrium problem every single year. Now they switch it up a little bit, but they always have equilibrium, at least one FRQ equilibrium problem. But the thing is, there are so many different types. So what I did is I put like 6 different types of problems, and we'll end up going through those. Quadratic, you won't need to use the quadratic on the AP exam, but there will be some problems that it's helpful. I'm going to try to see if I can get you not to focus on using the quadratic because people then end up spending 10 minutes on a problem that they could have done in 3. So Q versus K, we already did Q versus K. Remember the alligator mouth? And so it was like, if Q is less than K, then it was like, and the alligator would go this way, so you'd favor the products. And then if Q is greater than K, then it would favor the reactants. And so we'll come back to that as well. Okay, just sample problems. Okay, this is 17.4. Am I sharing my screen? Okay, good. Okay. So 17.4, this is chapter 16 that we're doing, okay? But I'm throwing section 17.4 in with the notes on this section because it kind of makes more sense to do it here. It's called Solubility Product. And so that's the last thing we'll do. And there are actually 4 different types of problems. So kind of like equilibrium all done together. So really, there are like 10 different types of problems that you can be asked on equilibrium. 4 from KSP, and then 6 from actual like just regular KEQ or KC or KP, whatever you want to call it, from equilibrium. Okay. All right, so let's get started with equilibrium and okay, so reactions are written as reactants, arrow, products. So this would be your reactant, this is your arrow, this is your product. One person last year, one person messed this up. Okay, and I was like, oh no. We're doing this in physical science right now. We're gonna do balanced equations. And that's something I keep repeating is wrap, wrap, wrap. Everybody say wrap. Even though this equation can go both directions, we still call the stuff on the left the reactants and the stuff on the right the products, okay? So just make sure that you have that down. Chemical reactants, people will say, well, I just got confused because there's a double arrow. I wasn't sure what direction. And they said that they put the products into the flask. It doesn't matter. So however they wrote the reaction down, that's reactants and those are products, okay? Although there are reactions which are blank, meaning the reactions occur in both directions, we call them reversible. So the reactions can be reversible. We still have reactants and products. Okay, so what happens in this first picture is we have sulfur dioxide reacting with oxygen to form sulfur trioxide. So if this is my reaction, and I tell you that I'm going to react these two to make this, what can you tell me about the SO3 at time 0? SO3 concentration at time 0. Yeah, it's 0. There isn't any. Very good. So down here, I'm going to put my SO3 concentration of SO3. Down here, those are brackets around it as 0. Okay, that's my SO3. Now, I don't know, I could add in a different amount of SO2 and O2. So this is where equilibrium can get a little bit tricky, because when I put into my flask, I could put equal moles of these in, but then I would have a limiting reagent, right? Because if I put equal moles, well, this is 2 for every one of these that react, then I should have some excess, right? So, but if I do react them equally, then what I'm going to do is I'm going to put my SO2 concentration up here. And if that's the case, I'm going to put my O2 concentration at halfway down. Okay, so what's going to happen is it's going to come to a position where it's comfortable, okay? And that's where equilibrium is. And equilibrium, again, changes when you have, depending on your pressure, what's your room pressure, what is the temperature. So equilibrium can be a little bit different depending on that. But what is equilibrium? Equilibrium is a position where a reaction comes to a point where there is no net change. We do not say that the reaction comes to a stop. So write the word stop and then cross it off. Okay? We do not say the reaction stopped. We say the reaction came to equilibrium, meaning it's just got no net change right now. They're changing, but it's just not a net change overall. Okay. So what's going to happen over time? Well, I'm going to expect my SO2 and my O2 concentrations to do what? To decrease over time. Okay. So I don't know where equilibrium sits, so I'm just going to kind of make this up. So let's say that my SO2 concentration ends up down here. And I'm going to draw a curved line coming down for my SO2 concentration. Okay. If this is a 2-to-1 ratio, where do you expect your O2 concentration to be at equilibrium? How much? Half as much. Good, Henry. Half as much. Why? Yeah, it's a 2-to-1 ratio. So then this should be half the amount. Again, it could be different if I started with more of it, okay? So let's come down there. Okay, and what do we expect to happen to the SO3 over time? It should increase. And I don't know where it's going to increase to, but we're going to put it over here. SO3, and I'm going to draw a curved line going up in that direction. So that's going to be increasing. Okay. So now this is the forward reaction. And now what I'm going to do is I'm going to reverse the reaction. And instead of putting reactants into the flask, I'm going to put products into the flask. Yes, I'm saying that, okay? Again, I know it sounds weird because you usually react things together and you call them reactants, but this is my reaction. I'm going to put the product into the flask, okay? Well, if that's the case, and I'm putting this in the flask, how much SO2 and O2 should I have at time 0? 0. So down here, I'm going to make 2 dots, one for my SO2 on top and the other one for my O2 underneath. Okay, and now my SO3, I'm charging it with the SO3, so I'm just going to put the SO3 up here. Okay, what can you tell me about what should be happening once it reaches equilibrium? What can you predict? Henry? I like it. And what else can you tell me? It's the same reaction. Gigi? Good, you are so smart. Very good. This equilibrium should be exactly the same as this equilibrium. It's almost like I could start you off anywhere, okay? So I put you anywhere. I put you in a different state. So you might be in Tennessee, you might be in Florida, you might be in Hawaii, you might be in Puerto Rico, wherever you are. But then home is where it is, right? You're going to come back home. So equilibrium is basically coming back home. So what's going to happen is my SO3 is going to be in the same position right here. My SO2 is going to be right on this line like it was before. And my O2 is going to be halfway of where it was before. And now I'm going to connect my dots with a curve, okay? So my O2 starts down here and curves. That looks like a linear line and not one linear. Curves there, curve there, and this one's going to curve here. Okay, so This could be a question. They could ask it as a multiple choice where they offer different pictures, different diagrams to ask you which one, according to this being equilibrium, which of the following diagrams would be correct. And in some of them, they might even have the product increasing instead or something like that, so they could change that up. But equilibrium is the same. So equilibrium, I'm going to put it in brackets. Equilibrium concentrations are the same as the forward reaction. Okay, so chemical equilibrium is a state in which the forward and reverse are taking place at the same rate. We already said this. There's no net change. A reaction can favor a certain formation. The equilibrium position indicates whether the products or the reactants, are favored at equilibrium. Michael, I don't know if you're okay. Do you want to? I don't know if you want to stand. Are you? I might be. I don't know if you want to stand. If you want to stand at the table thing, you can.
Okay, I'm good right now.
Okay. Okay. All right. So if there's, if you look at this arrow, I know it looks like kind of a half arrow, but this arrow is more in that direction, it's longer in that direction. That just means that B is favored. And we can see that this one's 99% versus 1%. The longer the two arrows indicates the favored direction. Okay. Favored simply means you have a greater concentration or amount of it. There's a higher or greater concentration or amount or pressure, whatever we want to call it. Okay, catalysts. In kinetics, we talked about catalysts where they lower the activation energy. So we know it lowers the activation energy, but it does the same lowering in both the forward and the reverse. So all that happens is you get to equilibrium faster. They get to equilibrium sooner. That's all it does, is it reduces the time it takes to get to equilibrium, but it doesn't actually change equilibrium. Okay, what factors affect equilibrium? So you know, it's Le Chatelier's principle. So I'm going to write this kind of twice. Le Chatelier's principle. And what I do is I write Le CTP. There's the C right there. There's the T and there's the P. Everybody say Le CTP. Le CTP. What is the C for? Changing the concentration. T, temperature, and P, pressure. Those are the three factors that affect it. Okay. So if you remember his name, Le Chatelier's principle with the P, with the principle, then you'll remember what three factors. Now, pressure is actually the opposite. So if you increase the pressure, then that's the same thing as decreasing the volume typically, okay? So if they tell you that some of you can hold it constant, but so volume, even though they didn't put volume on here, volume also changes, can alter your pressure too, okay? So when stress is applied, important word is stress, very important word. When stress is applied, the system shifts to relieve stress. And examples of stress are changing the concentration, changing the temperature, changing the pressure, or the volume. Okay, so we already talked about this, so let's go down to concentration and just try it out. It says, changing the amount of any reactant or product in a system is going to disturb equilibrium. Our bodies maintain an equilibrium between the amount of carbonic acid, which is H2CO3, to water and CO2. Okay, so what happens is in your blood, you actually have carbonic acid, but it's only a little bit of carbonic acid. Literally, it's like a 1% to 99% ratio between the two. So in physical science and in Gen Chem, we do these like little pop rockets, and it's like kind of like one of the big labs that they do, and they test different things out with them. But we take vinegar, which is acetic acid, and baking soda, and we mix them. And you've probably seen like volcano explosions and stuff like that with those. A lot of science fairs use this. A lot of kids use it for science fairs. And so what happens is you mix the two together, and then all of a sudden a gas is formed, and then it pops the top off. Well, the thing is that when you mix the two together, you don't actually see gas. It's a double displacement reaction. You get H2CO3. But, and it's easy to remember, you're going to want to remember this. Carbonic acid, because of the, you can see that there would be carbon dioxide, right? This immediately, almost immediately turns into CO2 and H2O anytime, okay? So carbonic acid wants to change into water and carbon. So if you form it, if you create it as a product, it actually doesn't stay this way. It turns right into this, and now you have a gas, and that gas builds up, and then you can pop things off. When we exercise vigorously, what do we exhale? Carbon dioxide. What happens is your body naturally wants to regulate, right? And so it's like, oh my gosh, you just got rid of the carbon dioxide and now my percents aren't right, okay? So what's gonna happen is the carbonic acid is gonna turn into CO2 and H2O. And sometimes our bodies don't work right, and so we can have high acid levels, for example. And so you want to make sure that if you are exhaling it, then you need to make more of this so that you have more of it in your blood and you don't have too high of an acid level, for example, okay? So as soon as the CO2 is added, let's say we actually add carbon dioxide. Let's say there's too much carbon dioxide and I'm not exhaling enough of the carbon dioxide, okay? If I'm not letting off the carbon dioxide, what's gonna happen is the carbon dioxide is gonna react with the water to make what? Carbonic acid, to form more H2CO3. So again, you just wanna make sure your levels are right, okay? And so when we say this, remember again, equilibrium, people always assume means that they're equal to each other because it sounds like it, but it's not. So equilibrium could be, it's just a state where there's no net change. You could have my reactant. So if I kind of look at this as like a seesaw, this is like reactants are up at the top here and my products are like heavy weighing down. I have more products. So it could look like this. It could look like this where my reactants completely turned into my products, okay? Or it could be like this, where my reactants are not turning into my products. You guys did a really nice job on the quiz, by the way. And so if that's the case, then maybe like it didn't have the right orientation, or maybe like I reacted them, but they don't have the correct activation energy, right? So there were different, the Fro thing, where maybe my reaction just didn't happen, okay? So I would need a higher temperature maybe, or something like that. If you add more, add a product or you take away reactant, what happens? What happens is when you add something, it's always going to shift opposite. If you take something away, you're going to put it back. Okay, so we're going to write this down really big. So if you add it, then shifts opposite. If you remove it or take it away, then you put it back. Same side. Okay. And this rule is going to apply to concentration and temperature. Okay. Pressure and volume are going to be a little bit different. I'll talk about that after. Okay. So it says if you add a product, so if I add to this side, which way is it going to shift? No. So what I'm going to do is I'm going to say shifts left, or you can also say favors the reactants. Okay, so my thing is though that R can be for right and R can be for reactants, which are opposite of each other. Reactants are on the left. So be careful with making sure that you're clear on like either write it out or say shifts versus favors, okay? If you remove a product or you add a reactant, so if I take away a product, I want to put it back, that's going to always favor the product. So shifts right or favors product. And there is no P, so that's fine. Okay. Farmers, I don't know if you know about this, about trying to naturally increase their yield of eggs. What farmers will do is they'll take the eggs away. If you take the eggs away, the hen will lay more. So if you take away a product, then the reactants will turn into more products, will create more products. When does concentration alter equilibrium? When you change the concentration. When concentration is changed. But I forgot to note this in first hour. Only for aqueous and gases. Solids and liquids, I'm going to come back and I'll say it on the next page too. Solids and liquids are not included. Okay. If you add more of a reactant, what did we say happens? If you add reactant, it's going to shift to the products, or shifts right. And if you take away a product, take away one of the products, you want to put it back. So what do? If you take away a product, you may have said it, I just didn't hear it. If you take away a product, you want to put it back on the same side, which is to the right. Shifts right again. Sorry, Jeffrey, I don't know if that's what you said. Okay, so now let's look at temperature. This is more of like the lab, don't worry about that, you don't have that. Oh, you guys, by the way, I'm going to minimize the picture so you can take pictures of it, and then you'll just be able to, because I forgot to publish it, I think. So, okay, increasing the temperature causes the equilibrium position to shift in a direction that relieves the stress. And they really do use the word stress in chemistry, okay? Oh, sure. Okay. Yep. Okay, so in this reaction here, I see heat here, which means it's an exothermic reaction. And if it's exothermic, my delta H would be negative in sign, okay? And so what happens is you have to take a look to see, because people will say, if you add heat, it's going to favor the reactants. If you take, no, it depends on whether it's exothermic or endothermic. You have to check to see where heat is and then treat it like a substance. So if I add heat, it's like I'm adding a product. So I always write it in to the reaction so that I can see. So how does temperature alter equilibrium? Well, anytime that you have an exothermic or endothermic reaction, if you change the temp, it changes the equilibrium position. Okay. What happens if you heat an exothermic reaction? So if I add heat to this one, which direction is it going to go? To the left. Awesome. Shifts left. What happens if you heat an endothermic reaction? So let's write one. A plus B plus heat yields C. So now I have heat on the reactant side. So if I heat this, which way is it going to go? To the right. Okay, and last thing is pressure. Okay. Changing the pressure only affects the system when you have an unequal mole ratio. Remember, the moles are the coefficients in a balanced equation, okay? But just like we said before, it's only for aqueous or gas. Solids and liquids are not included, okay? So when we did electrothermal, there were just a few people, but it was a multiple choice question. And I said, write the K. What would K be equal to, the expression for K? And people forgot and included the solids in there. We're just going too fast. So if it's a solid or a liquid, you don't include it. Okay. So we've got this reaction here. This would be a coefficient of 1. So I'm seeing a 1 and a 3, and this one has a 2. So we're doing pressure. What we do is we literally add up the moles on both sides. And now let me explain to you what my analogy is for this. Okay, so hold on, let's see what my time is. Perfect. Okay. So I grew up watching Star Wars. I have 3 brothers and we all loved Star Wars. Who's with me on Star Wars? Okay, good. All right, this is more than First Hour. This is good. Okay, so you will probably know better than I do because it's been years since I've actually watched it. But in one of the older episodes, but really like a newer, like happened more recently, but was an older movie, there's this scene where C-3PO and R2-D2 are up in this room and everybody else is in this garbage compactor, including like Chewbacca, and the walls are like coming in on them in this garbage compactor and they're trying to like turn it off, okay? And then there's this huge like snake looking thing that comes out and all this other stuff. So the way that I think of this is if the walls were coming in, do we want more stuff or less stuff in the room? We want less stuff. The more stuff there is, the more pressure. So if they start adding things in, adding in more moles of stuff, we're like, get out! We don't have a lot of room. We need our air. We need our space, right? But if the walls are bigger, then we've got more room. Then yeah, it's kind of like you can have more people. It's okay because we have our space. Okay. So in this example, it says you have a cylinder with a piston. You push the piston down, and what happens to the pressure when you push the piston down? It increases. The pressure increases. In other words, the volume has gone down. Okay, so remember from P1, V1 equals P2, V2? They're inversely related to each other. The system wants to relieve the stress. So there we go again with this relieving the stress. That's all Le Chatelier's principles on. Draw diagrams of the reactions and products to figure out which reaction is favored or which side is being favored here, okay? It's pretty easy. We're not even going to draw the pictures out. So in this situation here, if I decrease the volume or increase the pressure on the system, do I want the side with 4 moles or 2 moles? 2 moles. Favors products because 2 moles is less since the pressure is greater. Okay, so what I say, my saying is more is less and less is more. Okay, so more is less, more what? More moles or more, we do more pressure, it doesn't really matter. More pressure means we want less moles. Okay, or more moles, you want the side, if it's less pressure, you want the side with more moles. So it doesn't really matter which way you do it. Okay, and then again, what happens if you add a catalyst? How does it affect equilibrium? It doesn't change equilibrium. Doesn't change. What was the only thing that happens? You get there sooner. You get to equilibrium sooner. That's the only thing. It just takes less time to get to equilibrium. Okay, so let's try one of these and let's see how we do. So question 8, how is the equilibrium position of this reaction affected by the following changes? So we can see here, one of the things I want to make note of is in this one, they've got heat here. In this one, they've got 92 kilojoules. Come down to, oh, I didn't do it. Because sometimes what they would do is they might say, like, for example, in this one, they might say delta H is equal to negative 92 kilojoules. Since it's negative, you would know that it's exothermic and it would go on the right side, okay? So I just wanted to make sure that I made note of that. And so what you're gonna do is we're gonna check to see how you do. Everybody go ahead. Actually, the bell's gonna ring in like a minute anyway. So we didn't get to this in first hour, so this is perfect. So my plan